you for joining us today. We are excited to bring you this presentation on ETAP solutions for healthcare facilities. Healthcare facility power systems are required to operate consistently with high reliability and availability. They must not only be designed to be safe but respond satisfactorily during commissioning and operate reliably at any instant from that point forward. Electric power system is needed in healthcare facilities not only for medical devices, but also for essential electrical system equipment like lighting, air conditioning, telephone, public address, televisions, etc. The hospital power system life cycle starts with planning, design, construction, installation, testing, and commissioning. It then continues with ongoing testing and maintenance management. Facility services and maintenance department manage significant assets, including complex and numerous electrical installations, such as high voltage and multiple low voltage substations, diesel generators, distributed energy resources, energy storage, and mission critical loads. During the electrical system design, many unknown vulnerabilities may be uncovered and removed or mitigated, such as loss of incoming utility service, transfer switch failures, short circuits, lighting ballast failures, power distribution equipment failures, etc. Although most hospitals have some form of equipment failure procedures, a best practice can be validating that the failure procedures will pass the responding staff members' reality test the day the failure occurs. Therefore, it is prudent to recognize these failures and plan an appropriate response ahead of time. Are the most effective methods to ensure the power system quality and safety. This, of course, is in addition to electrical code safety standards constraint or accreditation-related compliance requirement that hospitals and other healthcare facilities must be able to meet. Architectural design firms, contractors, and consulting companies who design hospitals must take into account the regulations and operations of the facility in the long term. They are also asked to renew electrical installations in building and provide detailed engineering for planned expansion, retrofits, and upgrades. ETAP provides a comprehensive digital twin-based solutions from design to operation. Digital twin is the phrase used to describe a computerized or digital version of a physical assets and or process. The digital twin contains one or more sensors that collects data to represent real-time information about the physical assets. ETAP integrated single platform solutions allow for healthcare facility power system design within the safety and regulatory compliances. Further, it leverages the design knowledge with operations data to drive continuous risk assessment, situational intelligence, and remedial action. Let us take a closer look how. The electrical digital twin lifecycle we see here include automate and control, operate and optimize, monitor and predict. But this would not be possible without a strong foundation for electrical design and power system analysis. At the core of ETAP Digital Twin Foundations is the multi-dimensional platform. This is the same platform used by thousands of engineers around the world for modeling both greenfield and brownfield projects. It provides the end user with the ability to digitize and visualize an electrical network in multiple ways, such as in the middle, a geospatial view of electrical grid imported from existing ArcGIS or S3 database, saving hundreds of hours on recreating the model from scratch. On the left is what most of us are used to see, a typical radial view representing diagram or logical network view. And on the right is the network view. This provides the engineer and operator with a very clear organized view of a very large transmission and distribution network. Planning engineers have all three views available for quickly visualizing and performing analysis, all while displaying study results right on the selected view. Second is configuration. This is how we model multiple operating conditions or scenarios such as normal, emergency, single outage loading, various tie and switching scenarios. For those of you who perform arc flash analysis studies, you understand the importance of being able to model multiple operating conditions for a site and evaluating all of them to find the worst case scenario. Third is the data revision. This is what we use to model proposed new changes or modification, such as future expansion, what if scenarios, and mitigation studies before they are approved. Let us now see how the design digital journey looks like. Here we see the start of our roadmap, which begins with modeling. ETAP is based on multi-dimensional database, which allows for unlimited graphical presentations, status, configurations, data revisions, and time series analysis. Not only you are able to take advantage of our multi-dimensional database, but we also allow for collaborative modeling with NetPM, which allow for your team to model the one-line diagram at the same time, where you can update rating informations, add or remove devices, and run different studies and see these changes in real time. We also allow for data collection with our ETAP apps, which export your one-line diagram into a tablet or iPad, and you can compare or update your rating with your SFFF ratings. I will switch over to ETAP for live demonstrations and show you some of the applications. If you've got any question, feel free to ask. Now I'm opening an ETAP. To begin the modeling in ETAP, I can enable auto build, which allow for equidistant spacing between my devices and only allow appropriate devices to be connected to each other. I'm going to start by building a small model, and I can just click the power grid, then click the bus, the transformer, and the LV bus. And I will connect the motors. Now I can add the protection, the circuit breakers, and I can connect cables. So this is our ETAP auto build capability. It speeds up the process of creating a single line diagram. Now let's take a look at our libraries. I'll open up the circuit breaker, open up the library. So we have three different types that you could choose from. Molded case, power CB, this is what we refer to ACB, and insulated case. Based on the type that you select, then the manufacturer will be updated on the right side here. And once you select the manufacturer, then we will have all the model associated with the manufacturer in the middle. Once we select the model, at the very bottom, we'll have the solid state trip devices associated with this model. Now going into cables, we open up our cable library. So we can have huge list of cables that we can choose from. So the cables are based on the frequency. In this part of the world, we use 50 Hz, and you can select the LV cables to be about 1 kV. Then from here, you can choose whichever cables you like. Now going into the motor, I'm going to the nameplate rating. So we can start filling data here. We can choose from NEC standard motors or manufacturing motors, and then it gets updated. Say if I wanted to use the same motor details for motor number 2 and motor number 3, I just go and copy the data. Then I can go to motor number 2 and I just paste the data. Okay. Then the same thing for motor number 2, I wanted to transfer it to motor number 3. I just go to motor number arrows, click to motor number 3 and paste the data. So now all of our motors are 75 kilowatts rating. Okay. Now I'm going to switch over to back to the PowerPoint presentations. Once the modeling is completed, we can then proceed with model validation by running different analysis tools such as load flow, short circuit protections, and selectivity, AC and DC, high voltage arc flash, cable ampacity and sizing, underground raceway for our direct buried cables and duct banks, and ground grid protection. We can also verify that the sizing of our equipment are correct, and then we can create multiple output reports and compare them with our evaluators and analyzers. Lastly, we can create a macro to run a single study or multiple studies within the same project or multiple projects. I would like now to switch over to, again, another demo for ETAP. Uh, can you all see? Okay, it's coming. So now I will change this to different projects. I've already saved this as an example of a IC system. Over here, I'm open pre-built project that I've already has all the equipment ratings information filled out. I'm going to run a quick load flow calculations. You will see the real and reactive power flows results populated on the single line diagram, as well as the voltage percentage at each bus. I'll be going to here, then I'll run our load flow. We can change the unit from If you want to show the kilovolt, or you want to show the percentage. Now I can show also kilowatt only. I can show a kVAR only. I can show kilowatt and kVAR, and I can show kVA, as well as amps and kVA amps. But now what I would like to do is changing back to kilowatt and kVAR. At the bottom, we can see our critical and marginal alerts. For our critical alerts, we see that the circuit breaker 16 which is this circuit breaker here, was overloaded with the rating limit of 25 amps and operating at 634.1%. We will definitely need to resize this breaker. Below are our marginal results. It looks like our emergency switchboard and LV bus are operating under voltage. These alerts are based on the percent threshold that we have set in the load flow study case. Any device that exceeds 100% loading will generate a critical alert. In anything between 95 and 100% will generate a marginal alert. To the right, we have a threshold for our buses and over and under excited threshold for our generators and utilities. You could also create various revision by going to Data Manager, where you can change the rating of existing equipment. I have preloaded revision where I have updated the size of the overload circuit breaker when we first run the load flow. If you tick the base, and we can see the difference between the updated data and the base data. And then if we examine into detail, we will know what are the changes that we made to the circuit breaker number 16. In the circuit breaker number 16, I have increased the size of the circuit breaker frame rating as well as strip. Okay. Now I will run our load flow again, but now using the updated CB of 16. When we run this, then we'll see that our circuit breaker 16 is no more overloaded. In the configuration manager over here, we can have many configurations. Configuration actually refers to the status of the circuit breaker. For example, we can have a normal configurations. We could have single outage where this part of system is de-energized, and we could have many more. Now for the presentations, we could create another presentation called operator view 2. And at the operator view 1, we will use normal configurations. And then for the operator number 2, we will be having a single outage over here. Now if we run the load flow, we can compare the results for each one of these. Okay. Any questions?
No questions so far, Barry. I think it's no. I mean, if there is a question, I will also let you know.
All right, okay. Now we can change also the theme. If we don't like the, um, you know, the presentations here, we can change the our theme from to relay view, and we can also change the themes to study view. To change the theme, you just go to the colors and select the themes manager, and then you can have many colors. You can change all the colors that you want. We could also change the voltage level colors, assign certain network as areas, and color coordinate based on this. We can change the color for grounding connection lines, for grounding and earthing. And last, you can change also the font for your results, input annotations. Having done that, we can open up load analyzer. Load analyzer gives you the ability to examine the results of load flow analysis and compare them in one view. You can compare different study results case. No, sorry, this is arc flash. No, I should go to load flow. So this is the load flow study cases. We've got 5 study cases here, and then we can compare all those study cases in one view. When you have satisfied with the results of the studies, you can hit the export button. The results will be exported into Excel. This comes in handy when you need these tabulated results in your load flow report. ETAP also provides you with a scenario wizard where we can create a macro to run a single study or multiple studies within the same project. A scenario allows you to group all study options into one place. For this reason, scenarios are useful anytime you want to record a study to be executed. We have pre-recorded scenarios from arc flash to the harmonics to the motor starting and short circuit, as well as relay coordinations. When you want to revisit the projects in future, if you have forgotten study options you want to execute, Scenario Wizard will come in handy. Every project's file contains a scenario wizard. Scenarios are created and recorded in the scenario wizard and can be run individually at any time. A project can have an unlimited number of scenarios. From here onwards, I will be using scenarios to run our analysis. For example, I will start with a short circuit calculations. I'll be using the short circuit 909 duty. I can run the scenarios, and then once we run our device duty calculations, we can check our alerts view. And see our marginal and critical alerts based on the percent threshold that we set in the study case for short circuits. it looks like all our circuit breakers are having critical alerts. So this need to be reviewed and corrected. We can now generate an output report that can be exported to a crystal reports, PDF, Microsoft Word, rich text format, Microsoft Excel, and you can generate a complete report or input report that shows the rating of your input devices, a result report for your short circuit study, and an overall report summary. We'll take a look at the complete report, which includes the inputs, results, and summary. The first page contains all the summary buses in the project. Next, we are looking at the adjustment tolerances if they were used for the study. Here are the input ratings for our devices. In the middle, we have our short circuit results that were calculated during the study. At the end, we have a summary of interrupting and momentary duty calculations. Over here, ETAP shows that there are devices that exceeds the limits. For example, this red color indicates that the device with calculated duty exceeds the device capability. So we definitely need to look into this and correct it. And we go back to our ETAP. We can open the short circuit analyzer. We can see our results in the tabulated view through our analyzer. In this, we can see the output results that were generated during our short circuit study. In here, we can also compare multiple output reports, which will actually come in handy when we are talking about arc flash. Now going to our study wizards, we're going to run one arc flash study case. Just like load flow and short circuit, once we run the arc flash study, we can see the results populate on the single line diagram. We see the energy levels, arc flash boundary, incident energy, and fault clearing time. If you want to view the initial symmetrical bolted fault current on the one line, we can open up the display options and check this feature. This menu will also allow you to include more input ratings and annotations to your devices. You can check the desired annotations that we would like to see and will update accordingly. Here I've opened up the study case. We can include additional options when running the arc flash study, like calculating the load terminal fault current for a motor and include impedances for medium and low voltage motors. At the bottom, we can pick and choose which buses we like to fault all in one view rather than faulting each one individually on a single line. In the method tab, we can choose which standard we like to apply, like IEEE 1584-2018. We can choose the arc fault method if we will be evaluating a system over 15 kV. Let's take a look at the analyzer. To the left, we see all the generated output reports based on the various scenarios that we will already run for this project. On the right, we see the information for the elements we have selected on the left hand side. We can include additional devices information by checking the options. On the left, if we select the incident energy box and select the worst case, this will show the worst case based on the output reports. This comes in handy when you are generating the arc flash labels for your projects. Okay. We can then generate a label for the worst case incident energy for a single device or multiple device. I've selected 3 devices here. Here we have huge templates list that we can select from with labels from Bradley, every Dura labels and more. On this label, we'll see the arc flash boundary, incident energy, working distance, energy level, shock hazard, and appropriate working distances. You can also generate custom labels, work permits, and data sheets for your devices. Now I'm going to relay coordinations. I'll run also from the wizard. So this is the single line diagram where we have all the protection devices drawn on it. We can create a time current curves by selecting the network that we would like to evaluate. Here on the bottom right, I'm going to see all these protective devices. I'm going to add labels to this fuse so that we can see the settings. If I move the fuse curve to the left or right, we can see all the available sizes. I'm going to use zoom tools so that I can take a closer look at the 3cc curve. If I move the zoom box up and down, you will see that it updates on the right dynamically. If I wanted to see the time difference between the two curves, we can use the time difference tool to see the delta. This also moves and updates dynamically. I can include a crosshair that can trace a curve and show the current and time along the curve. You can create unlimited TCC curves and they will be saved in this pull down menu. Here's some of a TCC curve that were created for this project. To customize our TCC, we can go to plot options. We can change the axis, where we can set the scale of the X and Y coordinates. We can change our grid lines. We can change the line color and the major and minor grid. We can update the legends showing at the bottom. We can also assign a color for different device curves. If any information is missing, you can use device assessment tools to troubleshoot and verify that we have entered data for all of our protective devices. If any of the information is missing, then we'll get an entry for that specific device with a detailed description of what needs to be reviewed. Let's go back to our single line diagram. And look at the sequence of operations. This is a fault insertion tools. Where when we add a fault to our project, we will see the animations that provides the order in which protective devices will trip. If I place a fault here, in a sequence, we will trip the circuit breaker next to it. If this does not trip, then the next circuit breaker will trip. If this still does not trip, then the next circuit breaker. We can add many levels, unlimited levels of trip devices going upstream. The same thing can be checked when I place a fault here, and then this circuit breaker should trip the next circuit breaker and the next circuit breaker. This viewer shows a summary of which device trip first, and it goes down the list sequentially. We can see what are the protective devices that being triggered and at what time the circuit breaker trips. We can also have our protection zone viewer. If you were to see this VFD motors, no, that's not correct. That's not a good example. I'll show one good example. This is LV bus. So these are the protective devices that is related to this LV bus. Here we can see the full list of all devices connected to it. And then we can create a time current curve based on these devices. You can also create a device setting report for all the devices in your project. The device setting report will show all the settings for your protected devices such as fuse, inline overload relays, low voltage circuit breaker, solid state trip devices, overcurrent relays, overload heaters, overload relays, and recloser. If you would like to verify that our protection and coordination meets our customized design criteria in or industry guidelines like IEC standard, we can run auto star evaluations. To run the auto star evaluation, you just select all those elements in our system. Then press auto star evaluations. The green check marks means we pass the evaluation based on the selected rules. The red X mean that we fail in the evaluations due to violations from the rules. And then the orange exclamation points means that we observe the conditions which needs attention as it may change the result. On the right hand side, we are showing the condition for the status of that device. This table also works dynamically. We can take a look at the cables, and we see it has some violations, the orange exclamation marks. We can update the time current curve on the right hand side, and when we pass the evaluation, the status will automatically be updated in the table star auto, and it will get a green tick mark. I will proceed with the underground duct banks. Underground duct banks allows for cable derating analysis, specifically steady state temperature calculations, uniform ampacity calculations, uniform temperature calculations, cable sizing, and transient temperature calculations. You can specify the soil type, surrounding the raceway and the soil type inside. The raceway.